This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 140. The title of today's presentation is an introduction to GREMLIN, GOES radar estimation via machine learning to inform NWP. Our presenter is Kyle Hilburn, Research Associate from CIRA. Our facilitator is Chauncey Schultz, Science and Operations Officer from the National Weather Service, WFO, in Bismarck, North Dakota. Just a few reminders before we get started, that as you just heard, this session is being recorded. There will be an opportunity for Q&A after the presentation. If you're from a forecast office or regional headquarters, we specifically encourage your questions. And if you haven't signed in with your full name, please note your name when asking a question in the chat so we can follow up if necessary. Also, please check your spam folders for any communications from the TowerS team. Unfortunately, we've heard that some of our communications have ended up there recently. We're always looking for future presenters. If you are interested in being part of our Satellite Book Club seminar series, we'd love to have you, even if the topic of your presentation is not directly related to satellites, but maybe it's used as a secondary component, or you had a presentation from AMS or the NWA annual meeting you'd like to share. Please let us know. Contact our TowerS team for more information. And if you're looking for training materials, Brian Mata at the Office of the Chief Learning Officer can help with that. I'd like to thank our TowerS team, particularly Kushad Bowman, Lee Byerly, and our others, the Office of the Chief Learning Officer, GOES-R program, and JPSS program for their support of the book club. And again, thank you so much to our presenter, our facilitator, and all of you for being with us today. Before I introduce Kyle formally, I'd like to mention the GOES-R Mesosector Plan Survey. The TowerS team is looking into improvements on the GOES-R Mesosector request process. They welcome feedback from the field through the survey, which is a link in the chat. So please feel free to let us know your thoughts about meso requests. All right, let's dive into today's presentation. Kyle Hilburn completed a bachelor's in atmospheric science from the University of North Dakota in 2000, a master's in meteorology from Florida State University in 2002, and is currently working towards a Ph.D. at Colorado State University. Before coming to CIRA, Kyle worked in the private industry on microwave remote sensing with low Earth orbiting satellites. Kyle has been a scientist at CIRA since 2016, where he has been exploring the use of machine learning to get maximum value from the GOES observations. Kyle, we're glad to have you today.
Yeah, thank you so much, Jordan. It's a real honor to be speaking to the TowerS Satellite Book Club Seminar Series. Before I begin, I would like to acknowledge my NOAA collaborators, Amanda Back, Stephen Wygant, and Curtis Alexander. So the motivation for this work begins with the high-resolution rapid refresh model shown in this green box here. It's NOAA's current operational system, and it uses radar data over CONUS to initialize convection in the model. But NOAA is updating its numerical weather prediction models to use the Unified Forecast System framework. And as part of that, HER is going to be replaced by the Rapid Refresh Forecast System, shown in this yellow box, which you can see is much bigger than the HER domain, covering a lot of areas not served by radar coverage. Therefore, geostationary satellite products will be key both to initializing and to assessing this system. So for the GOES-R series, we have a lot of capabilities that we can bring to bear on this problem. We have 3 times more spectral resolution than the previous sensor, 4 times more spatial resolution, we have 5 times more temporal resolution, and we have lightning mapping. So the hypothesis of this work is that by harnessing the power of machine learning, we can use these capabilities to get radar everywhere for initializing convection in high-resolution models. Now, what is machine learning exactly? Machine learning is making big changes to our life every single day, and but it's not really as magic as it seems. Machine learning has 4 elements coming together. The first is the data set. The data is the most important thing. Ultimately, you can only learn what's in your data set. Then you have your model architecture, and that determines how you're learning information from the data, whether you are learning spatial information, temporal information, and so on. Then you have your loss function. This is an underappreciated component. This is really telling the network what to focus on and really determines what you're learning. And then you have your optimizer, and that actually helps train the model. So learning in machine learning is really just iteratively adjusting weights in a model. So this is the GREMLIN architecture shown in this diagram here. It's in the family of UNets, of convolutional neural networks. And we're calling it GREMLIN. I have Steve Miller to thank for that acronym. It stands for Gauss radar estimation via machine learning to inform NWP. So this is a convolutional neural network. The green boxes show the images across the network. The blue arrows show the convolutional layers. Now those are what are actually learning the spatial patterns in the data. Then we also have these red arrows on the left side and yellow arrows on the right side. And those are pooling and upsampling layers that are capturing multi-scale information in the imagery. A nice feature of machine learning is that it's able to provide data fusion capabilities. So it's fusing radiances from advanced baseline imager with lightning from the geostationary lightning mapper. Now for the inputs, the version 1 GREMLIN model is using the shortwave IR, the water vapor, the longwave IR, and GLM lightning group extent density. And then the model is being trained to multi-radar, multi-sensor, or MRMS, composite reflectivity. Now we've approached this problem using a hierarchy of data sets, which I show in this table here. The first data set was the CONUS-1 data set. You can see it only has about 200 images. It's sort of a toy data set, but that makes it really useful to explore concepts. These were manually selected cases based on important high-impact severe weather events, trying to maximize the diversity in the cases between time of day, geographic location. I just submitted that data set to Dryad last week, and so that'll be available shortly. The CONUS-2 data set is the data set used to train the version 1 GREMLIN model. That has about 2,000 images, and that was actually constructed automatically based on storm reports. This data set's available at this link here. And then finally is the CONUS-3 data set. This is the biggest data set of them all. It's sort of the kitchen sink in that it just takes samples every 15 minutes over CONUS. And 3 years of this data set have been released on Dryad already. I mentioned loss functions before. The GREMLIN model, when it's learning, it's minimizing the mean squared error. But there's different ways you can do that in terms of your probability of detection versus false alarm trade-off. And so this is a performance diagram which has probability of detection on the vertical axis and 1 minus the false alarm ratio on the horizontal axis. So because radar reflectivity has this distribution which falls off exponentially, where lower echoes are common, but stronger echoes are less common, if you train your model and you don't have any weight on the observations, you end up with the black curve, which falls in the underprediction part of this performance diagram. Now, you could say maybe I should just use a weighting on each observation of 1 over the probability distribution function. And that certainly produces somewhat better results. It does tend to overpredict the light echoes, and it still underpredicts the strong echoes. So by doing hyperparameter tuning, we can actually construct loss weights that are able to balance over and under prediction across the range of reflectivities. And qualitatively, we found that produced the most realistic looking radar images. So here's some examples from the GREMLIN data set. This is from CONUS-1. So the left is showing GREMLIN, and the right is showing the corresponding MRMS samples. And so you can see examples that have linear convection. GREMLIN does a pretty good job, especially at resolving that convective line. There's examples in here of isolated convection, and GREMLIN does tend to do very well with isolated convection and convective initiation. There's more complex scenes that also have stratiform areas, for example. You can see that Gremlin struggles a little bit in stratiform areas. For Gremlin to perform well, it either needs to have brightness temperature gradients or it needs to have lightning. And so if there's areas where you have areas that are cold and have not much texture, and you don't have lightning, Gremlin could struggle a little bit in those areas. But you see in general that Gremlin does provide a realistic picture of the radar reflectivity fields. So what exactly is Gremlin doing to make these predictions? We originally applied layer-wise relevance propagation, or LRP. That's a so-called explainable AI technique. And you can see, so up here in the top row, we have the inputs to the Gremlin model. In the row below that, we have the gradients, and this was just calculated for illustrative purposes. And then below that, here in this row, we have heat maps from layer-wise relevance propagation. And you can see, for example, if we look at band 13, that it's focusing in on strong brightness temperature gradients here, and also areas of cold brightness temperature. You can see it's also focusing on lightning as well. And one thing we found that if you actually turn off the lightning by setting it to 0 in the inputs, it changes how the network looks at the brightness temperatures. So when this machine learning is doing data fusion, it's considering all the inputs together and really getting the maximum value out of the observations. So in terms of the gradients, this is an important aspect of convolutional neural networks. If we start here with an example input from band 13 from GOES ABI, if we turn off the spatial context in our model, which we can do by using one-by-one filters, we can see this result here in panel 2. And you can see that while it resolves the kind of the cloud-no cloud boundary all right, you can see it's not resolving the strong echoes relative to MRMS truth shown over here in panel 4. So then if we turn the spatial context on, we can see that now the network is able to figure out where the stronger echoes are located. So it's this ability to use spatial context, which is really essential for this particular application, and is relevant to cases where we have cloudy and precipitating scenes, where the spatial information is providing new information that we're not using currently with data assimilation techniques. But what exactly is the spatial context? It's kind of a fuzzy phrase. So current work, which is actually in review right now at the AMS AIES journal, I actually found a way to approximate Gremlin using linear regression rather than machine learning. So the key insight here was in this convolutional neural network model, you have these different levels. These different levels actually correspond to an image pyramid, which is shown down here. And then the convolutional layers represent filter banks. Now in the convolutional neural network, those filters are learned. But in what I'm calling interpretable Gremlin, I'm actually prescribing the filters just with a few simple filters. And then I found that I can actually reproduce much of Gremlin's skill using the simple non-machine learning model. And what that was able to demonstrate was that the skill is coming from multi-resolution representation, which is provided by the image pyramid, information in the gradients and patterns in the brightness, temperatures, and lightning, which are captured by the filter bank, and then also the ability to represent nonlinearity. Now that's kind of all implicit in the convolutional neural network, but we can pull all those pieces together, pull all the pieces apart, and look at how they contribute to the accuracy of Gremlin. Now, lightning is very important to Gremlin, and so the fact that we have GLM on the GOES-R series is really crucial for this application. And this loop here, which we have geocolor with the lightning from GLM overlaid on it, is a really great example of why. You can see as we transition from day to night, we lose some information from ABI, but that lightning is able to see exactly where those strong echoes are located, day or night. And the reason the lightning is so valuable, if you can use some simple arguments to look at the relationship between updrafts, radar reflectivity, and the lightning flash rate. And that finds that the linear radar reflectivity factor is proportional to updraft to the 12th power, and that lightning flash rate is proportional to the updraft to the 5th power. So it's really the updrafts that are the key physical linkage here, and both of these quantities are strongly related to the updrafts. To take this a step further about how the relative contributions of lightning and the spatial information, I'm showing an example here. This is an example of the ABI input, the brightness temperature. Then we have the GLM lightning input. And here's the truth that we're trying to reproduce. And so again, when you turn off the spatial context and lightning, while you're able to delineate areas of cloud and no cloud, you miss out on those strong echoes. Now, if you leave the spatial context turned off, but you bring in lightning, you can see now you can resolve where stronger echoes are, but you're not really representing the weaker echo areas all that well. So when you turn on the spatial context, but don't have lightning, you can capture a lot of those strong echoes. And in fact, there is a lightning product from SIMS where they use the spatial information in ABI to predict what the lightning will be. But when you combine the spatial information lightning together, that is definitely the best situation where you have the most physical information coming together to find out where those echoes are located. Now for GREMLIN, everything I've shown is focused on the horizontal, on the 2D picture. But for initializing numerical weather prediction models, you actually need 3-dimensional fields of radar reflectivity, which are converted to latent heating to initialize the model. Now the problem is that the information content in GOES is primarily horizontal. It's not really providing vertically resolved information. So the strategy here was to treat this problem separately, where the horizontal picture is provided by the convolutional network by GREMLIN. And then the vertical information is provided by Dr. Yoonjin Lee's vertical profile model. And so she took, and you can see the lookup table visualized here in this multi-panel figure. So what she's done is she's taken WRF simulations in order to calculate relationships between the radar reflectivity and the observables. She used the same configuration as her with Thomson microphysics, and then constructed a lookup table for convective pixels. So how it works is first we run GREMLIN and get what the radar reflectivity is. Then we pass that and the brightness temperature into her lookup table model. And then it's able to give a vertical profile of the radar reflectivity. So let's look at an example. So in this example, we can see the GREMLIN radar reflectivity in this upper left panel. And we can see the corresponding MRMS composite reflectivity in this panel. Now, in the HER model, the first step is to convert that into latent heating, which is shown in these 2 bottom panels. And you can see that because GREMLIN tends to be smoother and have stronger convective cores, that the latent heating signature tends to be stronger and broader in area than the MRMS. So if we use the MRMS heating and the GREMLIN heating and put it into the model and run a forecast, you can see here's the results. Now for the storms up here in the northeastern corner, you can see both products give a pretty good initialization. But it's these cells here down in the southwestern part that you can see that GREMLIN is actually able to initialize things better than MRMS. Now both are able to initialize it better than no latent heating at all. But there's several reasons why this might be occurring. It could be the fact that GREMLIN is smoother or that it's stronger, or may have to do some details in the vertical profile model. Now, that was just one example, but we can look more broadly. So we ran a couple 1-week retrospective simulations, and these are some results showing the 30 dBz critical success index. And you can see over all of CONUS, the red curve is when you have no latent heating initialization. And whether you use the MRMS or GREMLIN-based latent heating initialization, you do see an improvement in the critical success index all the way out to 12 hours, in fact. although the improvement is certainly biggest in the first couple hours. Interestingly, though, if you look at just the western part of CONUS, west of 100 degrees longitude, where radar coverage is not as good, you can see that GREMLIN, which is this purple curve here, that it has higher CSI actually than using MRMS to initialize the model. So the hope here is that in areas where radar coverage is limited, that we can use GREMLIN to fill in those gaps. All right, so this brings us then to the current and future work and my involvement with Tower S and the GeoCloud program. So the focus of our project so far has been mainly on the CONUS region, where we have the best radar observations to compare our model against. But obviously the greatest value is where we don't have radar observations. So right now I'm working with Joe Zajic and others on implementing GREMLIN on the GOES full disk sector on NOAA GeoCloud. Now the processing on GeoCloud then will allow us to disseminate the product through Amazon Web Services by sending out notifications when new data are available. And it will also enable bringing this visualization into AWIPS. And so that's an exciting thing that that we'll be able to make available soon. And here's actually our first light image from a couple weeks ago when Joe came up here to CIRA and we were working on implementing GREMLIN on full disk. You can see I'm only providing it over the part of the ABI full disk where GLM is present. And now to validate things over the ocean, I'm going to be using the GPM DPR instrument, which is a satellite-borne radar, in order to make sure that GREMLIN is performing similarly well over the ocean. All right, so to summarize, the overall idea behind this is that to power transformative advancements, you need this convergence of three factors. At the base of the triangle is big data, but then using artificial intelligence to extract patterns from that data, and using cloud computing to be able to efficiently process that data and serve it out to users. So our work's demonstrated that by applying machine learning to satellite data, we can get new information and that we can use it to improve weather forecasts. So this is important for areas that don't have radar coverage, which isn't just the ocean, it's also parts of the Western US and also parts with lower population density. This is relevant to severe weather hazards that society faces and to supporting a weather-ready nation. So look forward soon to being able to provide full disk GREMLIN and getting feedback from operational partners. So with that, I'd like to thank everyone, acknowledge the GOES-R program for their support, and also NOAA RD-HPCS for their access to the Harris system that we used for training our machine learning. Thank you very much.
Thank you so much, Kyle. That was a fantastic presentation. I know I'm very excited about GREMLIN seeing this. I come from an area where indeed we do have poor radar coverage at times, and I know there's a lot of other folks out there like that. Obviously, you showed some great benefits to NWP that we'll have a chance to talk about here coming up in the next few minutes. So I would like to encourage everyone to stay on for a discussion that'll go on for about the next 20 minutes or so. We'd love participation, especially as Jordan mentioned earlier, from anybody that's in a field forecast office and regional headquarters or anybody that's out there attending today. We would ask that you would specify your full name in the chat room when you do ask a question in case there's any follow-ups to go on. I would also like to mention that next week, the Satellite Book Club on Thursday, April 27th, we will have Dr. Michael Pavlonis, a physical scientist with NESDA STAR, who's going to be discussing IMET satellite resources, so you don't want to miss that. And of course, we'll also always want to encourage folks to reach out to the Towers S team if you do need assistance with anything, in particular, Kashad, Emily, or Lee, with any questions that you may have or anything that they can help. There's also a chat room in the NWS chat room for them as well. So I see a few questions coming in already for us, Kyle, as we go forward. And one is from Dan Lindsay, and he's talking about that the one factor that affects lightning or the presence thereof is the absence or presence of aerosols. And so Dan's question for you is it possible that GREMLIN will be affected by clean versus dirty parts of the ocean at all?
Yeah, that's a great question, and it looks like it will be. So, you know, if you Contrast, say, the Atlantic Basin, or especially the Gulf of Mexico, where you have a much greater aerosol loading compared to the East Pacific. You have a lot less lightning in East Pacific storms. So where there is less lightning, that provides less clues to gremlin. Now, there might be some ways around that, though. We are looking at the lightning accumulation period. So when you have less lightning, you can integrate your lightning over a longer period. Currently, Gremlin is using 10 minutes for the full disk sector to accumulate over, but we could start to accumulate over longer periods if that helps. But yeah, you're right. Anything that lowers the amount of lightning for a given radar reflectivity can potentially affect gremlin.
Yeah, thank you so much, Kyle. That's a great question, Dan. Not being from somewhere near an ocean, I have not thought about that in particular, but makes good sense to me. Kyle, I'm going to go to another question that came to my mind, and then I see we have a question from Tim Schmidt, which I will get to in just a minute. But since you kind of touched on the full disk, and you talked about it, and of course in your presentation, I was curious if there are any challenges or opportunities in particular that come to mind when you're making a global version of Gremlin, when you're talking about using the full disk imagery.
Yeah, absolutely. So, over CONUS, you don't see quite all the regimes that you do over the full disk. And so one of the very first things we noticed is cold ground signatures at high latitudes. And so we've actually already brought in NWP surface temperature. And so, before you put data into a machine learning model, you have to scale that data. And as for a convolutional neural network, you usually scale it in the range 0 to 1. And with the original Gremlin model, we used 200K to 300K as our scaling. Now for warm season convection, that works pretty well because 300K was around the surface temperature and 200K is around the tropopause temperature. But when you go to full disk and you have cold land areas, using instead of a fixed lower bound or bottom bound of 300K, using the actual surface temperature from NWP, that's able to clean up most of those signatures. Now, for GOES, we have lightning, but if we want to extend Gremlin to a global product, to the full georing, we do face some challenges because now with Meteosat 3rd generation, we do have a lightning imager, but say Himawari, we don't. So if we want to bring this to make Gremlin a truly global product, we'll want to bring in, say, woolen lightning in order to be able to provide estimates where we have sensors that don't provide the lightning information.
Yeah, that absolutely makes good sense to me. And I'm coming from a colder part of the world, though maybe not as cold as some of the land surface areas that you're looking at and having some trouble with. I can certainly appreciate that. I want to go to Tim Schmidt's question now. And he was asking if the different parallax between the ABI and the GLM and the radar affects your results, especially when you get to larger satellite view angles, kind of talking about some of those same parts of the globe that we were just chatting about.
Yeah, that's a really great question. And that's why I want to do over ocean validation using DPR. Now, to a certain extent, restricting our attention to the GLM part of the full disk, we don't get to the very largest scan angles, but still, for the version 1 Gremlin, I've assumed a 10-kilometer cloud height to adjust for parallax. And doing that, it's better than doing nothing, but obviously you are incurring errors, especially if you have, say, shallow convection. So, the influence of that, especially as we go out to the larger angles, that is a key thing I want to assess as we make this transition from CONUS sector Gremlin to full disk Gremlin. Great question. Thank you so much.
Mike Stavish actually asked a question that I was going to ask, so it came to my mind too, which is about the initial field that you're looking at already. Is it'll be available in AWIPS like a synthetic radar image at any point, and then asking if we'll see this assimilated into the HER or the RRFS at the same time.
Okay, those are great questions. Thanks, Mike. So for the first one, working with the GeoCloud people, they're able to, by implementing it on GeoCloud, we're able to get it into AWIPS, and I think that's bypassing the LDM. I don't know all the details of that, and obviously we're still kind of putting all the pieces together in terms of the implementation. But my understanding is once we have it up and running in real time, we'll be able to do, for example, cloud reach sessions where we can all get together and look at a common AWIPS. I think it might be on a remote system, but yeah, there will be capabilities for that, and so as users determine if it's valuable for them, I'm pretty sure that it'll enable us to be able to provide it. But unfortunately, I'm not the expert on that. I would defer to Lee Byerly and others who are the AWIPS experts. But yes, that was part of the whole motivation of doing this onto GeoCloud, was to be able to kind of get the transition to AWIPS as part of that. Now, the other part of the question about assimilating the rapid refresh model, there's a lot going on right now in terms of that modeling suite. And in fact, they look to be actually transitioning from the latent heating based initialization to an actual variational data simulation. And so in that case, we want to use Gremlin to also provide uncertainties so that we could actually then blend both real and this synthetic radar reflectivity based on the uncertainty. And I've done some preliminary work where I actually extend the model, extend the loss function to be able to estimate uncertainties as well. So yeah, that is a hope, but right now they're actually working on other aspects of this transition from a radar-based initialization to an actual data simulation.
Yeah, thank you so much, Kyle. Those were questions that came to my mind too, as I mentioned, as being someone in the field. Thought it's very interesting. I see Lee Byerly did chime in and say that this indeed could be sent out via the LDM pass through the regions if that was coordinated and approved. I'm sure many WFOs in the field will be asking for this kind of data. And I was also very curious about, if you had done any testing on combining sort of the real radar data with the Gremlin data and scaling that into an ensemble framework. One thing that came to my mind, not only from a larger scale NWP perspective, but also getting more into that RRFS timeframe or the Warn-On Forecast System timeframe. When I know some of their struggles are with the modeling system there in the pre-CAI convective initiation type of phase. And so it sounds like you're already kind of traveling down some of that path. So very interesting. Scott Lindstrom, yeah, go ahead.
I just wanted to say kind of along those lines. So, because Gremlin is looking at cloud top signatures, it actually gives you a little bit of lead time over the radar. And so especially in situations like convective initialization, I think that's also a contributor to the skills. The fact that looking at cloud top gives you just a little bit of lead time between when you can see it versus when you actually get, drops that are big enough for a radar signature.
Yeah, that makes sense to me. And that, I had noticed that you kind of alluded to and did some work, taking out the lightning and kind of comparing, noticing that there's data in the ABI that can be related to that. I know in the field, we've been using the Lightning Cast product, and we've seen some good success with that, at least in my office, where indeed we get hints of, where CI is going to occur earlier in the phase with the ABI. So it makes sense that that stuff all ties together. And I could see there being value in Gremlin and those sorts of realms, even in the field where maybe we have better radar data. Although my office is one of those areas that, we still have radar coverage issues, right? Especially with shallow precipitation. And I guess one of the questions that I had for you was if you've thought about in any sort of future work, or if there's any possibility of working on something like Gremlin or expanding Gremlin to maybe try and handle some of those stratiform non-lightning type of scenarios like light snow events as well at all.
Yeah, and to that end is kind of bringing Gremlin into another project here at CIRA. We're considering bringing in passive microwave information. Now, you don't always have that, but where you do have that, it can provide some help in those situations where the ghost radiances might not completely constrain the problem. You may not have a lot of lightning. Passive microwave can help. So yeah, that is something we're thinking about.
Yeah, that's great to know. It was just definitely something that came to mind. Exciting stuff for sure. And I guess related to that, going back to Scott Lindstrom's question, sorry, Scott, took a couple minutes to get back to you. But Scott's asking, if you have these synthetic radar images from Gremlin, what might you learn from a comparison to level 2 rain rate?
That's a good question. So, at CSU here, Eric Goldenstern, who's a PhD student, he's taken the GREMLIN model and applied it to precipitation. So instead of training to radar reflectivity, he trained it directly to precipitation. And what he found was that, even though these seem like similar problems, there's a lot of subtle differences, both in the statistics of reflectivity versus precipitation. But with precipitation, you have the humidity near the surface is also a factor, and you don't really know anything about that from GOES. So I think if you can do precipitation, you're also going to need to bring in some NWP information to get vertically resolved humidity knowledge, because what you're seeing in terms of composite reflectivity versus in terms of what's actually falling at the surface are quite different, and you need to account for different physical processes. So, it is tempting to say, oh, we have a synthetic radar product, let's put it through a ZR and make precipitation. But I think, as we all know from experience, that there are a lot of other complications in terms of ZR relationships.
Yeah, thank you, Kyle. That makes good sense to me as well. And I was thinking back, that kind of relates to the NewCaps problem in the boundary layer, in a sense, right? Where the ABI data does fantastic, or the satellite-based data does fantastic, but maybe those boundary layer things being a role in that. And you hinted at, needing additional information like the RH in the boundary layer. And I guess a follow-on question that I had for you is if you've considered, sort of related to that, any other inputs to help along with GREMLIN, and maybe on the satellite sense. I know you talked about NWP using some of that at the higher latitudes and things like that. Did you look at other inputs, make RGBs, for example, or is there any data that's really not necessarily coming from the RGBs that you're not getting from the base ABI imagery?
Yeah, those are some good points. So for starters, what I didn't show here is that, bringing in the visible channel, band 2, and also bringing in the ice sensitive bands like band 5 or 6 really are helpful. And those are, of course, the inputs to the day cloud phase. And during the daytime, those can provide a lot of additional skill, actually. So in terms of the results I've presented today, this is the version 1 GREMLIN that's really just the IR and the lightning. But bringing in those other inputs during the day helps. And in addition to the passive microwave, which I mentioned earlier, one product that I think could actually really make some big help would be John Forsyth's advected layered precipitable water product, because that's telling you about the moisture at different levels. And I think that could help tease out some of these situations where the ABI data aren't completely constraining the answer, and bringing in the humidity information, I think, might be able to help in those cases.
Yeah, thank you very much. And I suspect that there are a lot of field folks whose ears just perked up when you mentioned ALPW, since I know that gets used quite a bit, especially in certain offices, and certainly I can imagine some great combinations that could be done with GREMLIN and those sorts of things. It looks like the questions are starting to slow down. I'll pause and see if anybody else has another question. Kyle, did you have anything else that you wanted to add as we kind of get close to wrapping things up?
No, thank you. I just wanted to say thanks for this opportunity. It was really great to be able to present this to the Satellite Book Club.
Yeah, thank you so much. This has been fantastic, very interesting. I know I'm excited for this, even in an area that's not oceanic, because I see a lot of potential for this going forward. So at this point, I'm going to pass it back over to Jordan Girth for some final remarks.
All right, thank you so much for that, Chauncey and Kyle. Great presentation, really exciting to see this work, filling in some of the information gaps that our forecasters have. So look forward to seeing the progress on this as it becomes more mature. Next week, the Satellite Book Club continues. We're going to have Dr. Michael Pavlonis from NESDA STAR is going to discuss IMET satellite resources. If you need any other information from the Tower S team related to the book club or configuration of satellite products in your AWIPS, Lee Byerly, Kishore Bowman, and Emily Maddox are standing by. So we will leave it there for today. I really appreciate everybody's attendance. Thanks so much again to our presenter, facilitator, and all of you for being with us today. Hope your spring is going well, and I'll talk to you again next week. That's all for this week's Satellite Book Club. Bye-bye.